I think we're at 10 o'clock now, so let's just get started. Whoops. Okay, so this is our Lab 2 demo. Thank you for coming. And in this lab, what we're going to be doing is measuring the energy content of food, or in other words, food calories. And we're going to be doing this using the first law of thermodynamics, which you should already be familiar with, whether you're in my class or otherwise, and also a bomb calorimeter. So it is called a bomb calorimeter because it is a bomb. So we are going to be building bombs of food in this lab, which is very fun. And this is what the equipment looks like. I have a picture up here, but we have two setups over on the wall over there that you can see. And we'll talk about that in a lot more detail in just a second. So food calories, I'm sure you're all very familiar with looking at nutrition labels throughout your life, where, you know, we see things like serving size, nutrition facts, and then the number of total calories in the food. So a couple things to say about this, because this isn't directly what we're used to talking about in terms of energy. There's a bit of a unit conversion that we need to be aware of, which is the following. So 1 calorie is equal to, we abbreviate this as 1 cal, and that is equal to 4.184 joules. So that is our conversion from calorie to joule. And 1 food calorie, which is what's on a nutrition label, is equal to 1 kilocalorie, it turns out. And so for this example, so for 280 food calories, this is the same thing as 280 kilocalories times 1 kilocalorie is 1.8, oops, sorry, 4.184 times 10 to the 3 kilojoules. So this is 1,171.52 kilojoules. Okay. All right, just as an example. So we can convert from food calories to joules or kilojoules. And then in this lab, the goal of the lab is the following. Calculate the energy content of a food sample. Your food sample will be initially unknown what it is. And then given a list of 4 options of what it could be, we want to figure out what type of food we think it was, okay? All right. Okay, so I have in here some sketches of kind of what the parts of the bomb calorimeter. So the whole system is here on the left. So we have a water bath. So essentially there's a bucket. That does not show up. Maybe. So this part here is a water bath. So it's essentially a pail that we're gonna put water into. And we're going to be measuring the temperature of that water surrounding the bomb. So the bomb itself is here. And this is a cross-sectional view of it. So it's a high-pressure oxygen combustion bomb. If anyone's ever used an Instant Pot or a pressure cooker, it's essentially that, but we're passing electrodes into it so we can combust the food sample inside. And the water bath also has a stirrer on it. So this stirs the water. This is the thermocouple that measures the temperature. All right, and so the reason that we want to stir it is we want to make sure that we're getting a good temperature measurement. So we're only measuring the water temperature in one specific location. So we want to make sure that it's a well-mixed water sample so that the temperature is reasonable approximation of the whole thing. So this is kind of an overview of the system. So what I'm going to do next is I am going to walk us through the experiment. All right, so we have two setups here. This is setup number 1, so it'll be marked on the equipment on a couple of different pieces of equipment. This one's number 1. This one is number 2. So the first thing that you want to do is you're going to sign up for number 1 or number 2, but you want to make sure you make a note of which one that you're using because they have different calibrations, which we'll talk about in just a minute. But you'll sign up for one or the other and then make note of which one you have. The next thing that you're going to do is you are going to come over to the front of the lab and you will pick a food sample. So it doesn't matter which one you picked, whatever one your heart desires you to pick, and just make note of the number on the top. All right, so this one is food sample 30. So on our lab sign up page, you may have noticed that there is a tab called food sample list. So that's food sample list is basically a column of numbers. Those are going to be correlated to these sample numbers. And then there will be masses in there that you're going to need to use for your lab calculations. So the mass of all the things in here have already been calculated and tabulated in there for you. So that's why I want to make sure that you note down which number that you have. Okay, so write down your food sample, write down which unit you're using. That's the first step. And then the second thing that you're going to do is you are going to take your water bath container. And you're going to fill it with 2 liters or 2,000 milliliters of DI water. So that's deionized water, essentially water that is completely pure. So we're using an assumption that we're using pure water in our calculations. So we want to use that water for the experiment. So that is up in the front of the room. Use a graduated cylinder to fill this up. The TAs should be keeping an eye on these being full. If you find that you come here and they're getting low or they're getting low by the time you are done with the experiment, can you please email them and let them know to refill? So each of these is 1,000 milliliters. So I'm going to fill this up twice and then put it into the water bath. All right, and then always measure based on the meniscus. So it's moving. Okay, that's pretty good. So here's 1,000 milliliters. Now we just want one more. Okay, and here's our second 1,000 milliliters. All right. Okay, so now that we have our 2 liters of water in here, I am going to set this into this piece of equipment, and you're going to want to make sure that you have there's kind of a little circle on the bottom of this. Make sure it's to the right. So then I think it's only number 2. So make sure no, never mind. There's a number on both sides. I was gonna say if the number 2 is in the front, you're good, but there are no sides. All right. Okay, so I've got that in there. The next thing that we want to do is we want to set up our food sample inside the high pressure oxygen bomb. So essentially, this is kind of the bottom part of it, of our container. This is the lid. and then we're gonna tighten it on top with this, okay? The other piece that we're gonna use is this crucible. So this is where it's just like a little cup. This is where we're gonna put our food sample. And so now when you open up your food sample container, you will notice that there is a piece of whey paper in here, a little fuse wire, which is gonna be hard to see from far away from me, and then a gelatin capsule, so it looks like a little pill of crushed up food. All right. The fuse wire we can touch with our hands, that's not a problem, we have to do that to set it up, but the food capsule we wanna transfer with the whey paper and not use our fingers, so the oils on your finger obviously contain energy, it's an oil, so we want to avoid touching the gelatin. All right, so I'm going to set my crucible cup in this little holder right here. And I'm going to, I find that it's easier to orient it like this, so it pulls out a little easier without having to twist it when the sample's in there. This part's a little bit like operation, but you just want to kind of scoop up your sample with the paper and then get it into the cup without touching it, okay? The next part is adding our fuse wire. So, okay, so it's a very tiny little piece of wire. And how we're gonna connect it is we're gonna move up these collars, and there's a tiny little hole. So we're gonna thread the ends of the wire through both holes and then move the collars back down to hold them in place. And the idea here is that we want to connect the wire to both of these leads because we're gonna connect electrodes up here. And then we want the wire to be touching our food sample, but not the edge of this metal cup. So if it's touching the edge of the metal cup, it'll short out on the cup and it won't actually ignite the food. So that's important. Okay, so again, just to connect these, you lift up the little collar right here, put the wire through the hole. On both sides. And then put the collar back down. And then typically, I find that it works fairly well to kind of put a little bit of a twist in the wire so that it's reaching down into that little cup to touch the food, but not the sides of the cup. Okay, so if you guys want to come and look at this, that's fine. Feel free to come over and have a look. Okay, the next thing that we're going to do is we want to very carefully move this lid and put it onto the bottom part of the bomb. So that's part of the reason why I twisted this the other way, so I can kind of carefully lift this up out of the holder and get it into here without disturbing the wire and food sample setup that I've just done. This is a little bit heavy, so twisting it around and moving it out, I find to be a little challenging to keep it perfectly still. And then you're just gonna set this in here. You take the lid and this just screws out up. All right, so you wanna screw this on, careful to not like jostle it. And then this should be, you know, kind of hand tight. Okay. There's quite a bit of thread, so it takes a minute. Okay, there we go. Okay, so here's our bomb setup. So that's all complete. Now, the next part of this experiment is probably the trickiest, well, maybe not trickiest, but the most likely for you to make a mistake on accident. And that is we need to charge our bomb with oxygen, right? So we need oxygen to do combustion. So we're gonna pressurize this container with oxygen, just like a pressure cooker. All right, and so we're gonna do that using either one of these oxygen tanks. And at the end of the hose line is this fitting. It'll be kind of hard to see from there. You can come take a look afterwards if you'd like, but there's a little black O-ring inside of here. If you don't follow all the steps to release the pressure in this line after you've filled the bomb and you try to pull this off, the O-ring's gonna go flying. If that happens, then you won't be able to pressurize the system like for the next group. So if you get here and you notice the O-ring's missing, or you try to pressurize it and it just hisses at you, that means the O-ring's gone. So you'll have to contact a TA or one of us, okay? So just be very careful to make sure that you don't do that just for the good of all the groups. Okay, so, and since, you know, we're dealing with pressurized things and an O-ring could fly off of here, I would suggest, those are filthy, wearing safety glasses. They're all super gross. I'll wash these off. So nothing should fly off if you do it correctly, but you know, if you forget to release the pressure, it could. So we should protect our eyes. So what we're gonna do is I would suggest having this lined up with this smaller valve opening towards you, and that's where this connects. So you just press this on, just like that. Doesn't screw or anything. You just press it on, and then we open up the oxygen tank. Maybe it was already open. Okay, it's already open, so that's fine. And then we're going to open this valve until we get to 27 atmospheres of oxygen in here, okay? So it doesn't take too much, just open it slightly and it goes fairly quickly. So it's just, you know, a tiny turn will do just fine. And then a bit more. Okay, and then once you have it filled up, I'm a little under 27 at the moment, that's okay. You're gonna close this valve off. And that means that we have, this is reading how much pressure is inside the bomb, okay? So the next thing we wanna do is we have, you know, 25 atmospheres of pressure in this line. So if we were to take this off, we would release all that air very quickly, which is what would cause that little black O-ring to fly out. So what we're gonna do is we're gonna release that pressure that's in the hose by just opening this, okay? And once we've done that, then we can take this off without an issue. All right, O-ring's still in there, everything's good. Okay, any questions on that step? Okay, so I'm gonna close up the tank now that I'm done with it. And I'll close this one too. Okay. Okay, so the next thing that we want to do is we want to put our bomb inside the water bath. We are going to do that using these tongs. So if you squeeze it, they open up, and there are little holes on the edge of this cap that this will fit into. You're going to want to be very careful when you're doing this so that we're not disturbing the sample inside here. Obviously we can't see it anymore, so we want to be careful that we're not messing it up just in case. And also just so you're aware, this thing is pretty heavy. So we're gonna just very carefully take it and lift it into the bath, and the bottom of this will line up with the little circle inside of here. Okay. Make sure you keep all the water inside the system, so if the tongs get wet, just kind of tap them off on the side. And then the entire bomb is going to be covered with water. That's by design, so don't be worried about that. And then the next thing that we're going to do is we're going to plug in the electrodes on the top, which we'll do right through the water, and that's fine as well. Do you guys want to see it? I know you can't really see what I'm doing very well from sitting there, so if you want to take a gander, that would be fine. All right, so hopefully, well, maybe you didn't, but hopefully you noticed that there is a bit more space on the left-hand side in the water bath than on the right-hand side. That's by design, because this is the lid that's going to go on top. So here is our stirrer. So this is a little turbine. And then we have our thermocouple right here. So we need a little extra space for this moving blade to fit in here. So we're going to set this on top. All right, and then the next thing that we're going to do is we're going to install the belt. So this is what's actually going to turn the stirrer. So it just connects here and here, like so. All right, I'm going to turn on, this is our thermocouple readout. So I will just turn this on to start with. And then I'm also going to turn on the stirrer. So that is with this knob on the top. I'm not gonna wait like how you should for the actual lab, but we want for the water to be at, well mixed room temperature before we stop. So you're gonna let it stir and sit like this for about 5 minutes, okay? And you'll see that the temperature kind of settles down eventually. Okay. So the name of the game of this experiment is essentially the following. So we are going to ignite our sample and then we're going to monitor what the water temperature does. There is a sample kind of spreadsheet for how you should collect your data at what time intervals in the lab handout. And so I would suggest kind of a efficient way of doing this. You should all have teams of 4. So this is kind of a 3-man operation in my opinion. So you will have somebody that is watching the stopwatch, someone that's watching the temperature, and then essentially a scribe. So whenever the stopwatch person says go, the person watching the temperature can read it out and then the scribe writes it down. Okay, that seems to be a smooth way to do it. So that's what I would recommend. And so you start doing that process as soon as you ignite the sample. Would anybody like to do the honors? Okay. So it's a little anticlimactic, but all we're going to do is we're going to press this black button and just hold it down until the red light comes on. So it should be like a second.
In 3, 2, 1.
That's it. So it's not loud. So our sample is now hopefully fully ignited. And the energy from that reaction should be transferring through heat to our water bath. So our water sample temperature should be going up. I'll show you exactly kind of how to expect that plot to look, but essentially it'll rise kind of slowly at first, and then it'll really pick up. It'll hit some peak temperature and then start to cool off, okay? So right now we're at 21.3 degrees C, and then I'll keep this going and we can come back and look at it in just a second. Okay, I put in this handout kind of my scaled down version of the instructions. So this is what I used to follow when I, lead the demonstration. There's a more verbose set of instructions in the lab handout that should tell you to do essentially the exact same thing. So that's what that is. So I said at the very beginning that we're going to use the first law of thermodynamics to figure out what our energy sample is. And so right now, essentially what we're going to do is we're going to go from the first law of thermodynamics and figure out how we can use essentially the temperature values that we're recording over time to figure out the energy of that sample. Okay, so the first law of thermodynamics is the energy at some state 2 minus the energy at some state 1 is equal to energy in minus energy out. All right, so keep in mind, E is total energy. Which we can break down into the following essentially energy buckets. So we have total internal energy, plus kinetic energy and potential energy, right? What do we think about, obviously there's internal energy in this system. That's kind of what we're trying to find, right? So we know we need to keep U as a term, but what do we think about kinetic energy and potential energy for that system? Do we need them? No. Our system's not like flying around and changing its velocity. It's also not moving up or down with respect to gravity, so we can get rid of both of these. So we will neglect those for this particular system. And then that means that our E2 minus E1 side of the equation is just U2 minus U1. And just so I'm not writing U a million times and to be consistent with the handout, I'm going to call this delta U12. So this is the change in internal energy for our process 1 to 2. Okay. We can break this down into the different parts of our system that hold internal energy. So we have a change in internal energy of our sample. We have the change in internal energy of our fuse. We have the change in internal energy of the water. And then we have the change in energy of the bomb. And I'm actually going to make this subscript just W. But this is the water. Does that make sense? Okay. Now let's talk about the right-hand side of the equation. So we have E in minus E out. What energy are we putting into our system? Anything? So the food is energy, but it's the U terms that we already talked about on the other side. Yeah.
The energy that we're dumping via the wire.
Yes. So we have electrical work being input, right, through the ignition. Very good. Thank you. So E in is the electrical work input. So I'm going to call this WE. So this is electrical work input via the fuse wire. And then our energy coming out is going to be QB. So this is the heat lost by the system. Okay. Okay, so let's put together our right hand and left hand side again. So on the left hand side, we have the change in internal energy of our sample, plus the change in internal energy of our fuse, plus the change in internal energy of the water, plus the change in internal energy of the bomb itself. And then that is equal to our right-hand side, which is the work of the electricity going in through the fuse, through ignition, minus QB. So that is the heat lost by the system. Okay. So I'm going to rearrange this slightly so that I have on my left-hand side, I'm going to have all the things that cause the temperature rise to happen. And then everything that's related to combustion, I'm going to put on the right-hand side. Okay, so the temperature rise terms are the change of internal energy of the water, the change in internal energy of the bomb, and then the heat transfer term, QB. So this is all resulting temp rise terms. And then on the other side, I'm going to have everything related to combustion. So I have minus change in internal energy of the sample, minus change in internal energy of the fuse, and then the work input by the electricity. So this is combustion terms. Okay. In my class anyways, we are going to talk about specific heat today in class. Oops. And so this is a little bit of a teaser for what you're going to learn soon. But we can rewrite this change of internal energy for the water and for the bomb itself in the following way. So essentially, this change in internal energy is related to the mass of that thing times the specific heat of the substance. So CVB is the specific heat of the bomb. And then CVW is the specific heat of water. All right, so this is essentially a material property. All right, so different materials have different specific heats. So we have a different specific heat for the bomb and then a different specific heat for the water itself. Okay, so that means that we can substitute those expressions into our first two terms on the left-hand side. And then I will also make a note that will help me with the algebra in just a second. And that note is that QB is proportional to delta T. So if, what I mean by that is if I were to plot QB versus delta T, I would get a line. All right. And this slope then is a constant. So I can say that QB over delta T is a constant. Okay. So what I'm going to do now is I'm going to just substitute these expressions in for the left-hand side. So I have the mass of the water times the specific volume of the water times T2 minus T1 plus mass of the bomb times the specific volume of the bomb times T2 minus T1. And then I also have I'm going to write QB as QB divided by T2 minus T1 times T2 minus T1. All right, because then I can factor a T2 minus T1 out of all three of these terms, right? Okay, and then let me see if I can move this over a teeny weeny bit. All right, okay. So then on the right-hand side, we still have our minus delta US minus delta UF plus WE. Okay. So I'm going to just factor out my T2 minus T1 on the left-hand side. So I have MW CVW plus MB CVB plus QB over T2 minus T1. And then all those terms are multiplied by T2 minus T1. Okay. And then just remember that this term is a constant. And then CV for both the bomb and the water, those are material properties, so those are constants. And then we have a closed system, right? So the mass of the water and the mass of the bomb, those should be constant as well, right? So this whole thing in the brackets is a constant. And what we can do with that constant is we can say, okay, this whole group in the brackets is a lumped thermal capacitance of the calorimeter. All right, so we're going to call this C thermal, so this is thermal capacitance and it's of the calorimeter. All right, the reason that you had to write down which setup you're using, number one or number two, is because this is calculated through a calibration procedure. So the value of the capacitance for the calorimeters is given to you, but it's different for one versus two, okay? So for unit one, and this is in the handout, but I'll write it down for you anyways, is 243.9 plus or minus 18 calories per degree C. And then for number two, it is 2,427.0 plus or minus 21 calories per degree C. All right, so we're giving you the value as well as the uncertainty for that. Okay. Let's do a little bit of work on this right-hand side. So if I have a look at this term right here, so minus delta US is the same thing as the minus of the internal energy of our products. So this is what is left over after our reaction has taken place, minus our internal energy of the reactants. So essentially what we started with, right? I'm just gonna pull that minus sign through the parentheses. So I have U reactants minus U products, right? And this difference in energy is just the total energy released from the sample. All right, so I'm going to write this a slightly different way because we have the mass of our sample, right? So we're going to say that this is just the mass of our sample times the energy released from the specific energy released from the sample. Okay. In a similar way, we can rewrite UF, delta UF. So minus delta UF is equal to U of the internal energy of the reactant minus the internal energy of the product. And this is for the fuse wire. We can rewrite this in a slightly different way. So now we're going to write this using the length of the fuse wire that is remaining times the energy, the specific energy of the fuse wire. And this is something that we give to you as well. So this is, actually, hang on. We don't give you this quite, but close. So 1 second. All right, so this is essentially, this LF is the length of your fuse wire initially minus the length of the fuse wire after the combustion. So when we take that thing apart, I'm going to show you that not all of the fuse wire has burned. So we want to measure what's left over at the end. Okay. We'll talk about that in a second. Okay. So let's put this all back together. So we have our lumped capacitance. So we have thermal capacitance of the calorimeter times T2 minus T1 is equal to MS ES plus LF EF plus we had work of our electricity, right? So I can write this work of the electricity as LF times a specific work of the fuse. It's really hard to make capital and lowercase w's look distinguishable from each other. So that's a little w. There, I guess that's a little bit better. Fixed it. Okay. Oh, no, one more. All right, there we go. Okay. So since I can rewrite that as LF times little WF, I'm going to group the LFs with EF and little WF. Okay. So I have at the very end of this C TH cal times the temperature difference is equal to MS ES plus LF times the quantity of EF plus lowercase wf. Okay. And this quantity altogether is what we give you. So we're going to call this E equivalent for the fuse. And this is provided to you as 2.3 calories per centimeter. So this is given. All right. So if we take a look at what's given to us, we have this. We have this. We have this. And then we are measuring in the lab LF. And we're also measuring our temperature, right? And then ultimately what we want to find is the energy of our sample, right? So this is where we end up kind of at the end of the theoretical calculation, but I will give you a word of caution. So if you remember, our sample is inside a gelatin capsule, right? So we need to isolate the food from the gelatin. So in this case, ES is E food plus E gelatin. And E gelatin is equal to 4,600 calories per gram. And this is given. Okay. So essentially we want to find this guy. And this is given. Any questions on that? No, it's okay. Okay, so let's go back and look at what our system looks like. We're going to take this apart. Does anybody remember what temperature I said this was initially? I can't remember anymore.
21.3 degrees Celsius.
Okay, it's now 22.19. So it is higher. I don't think I mentioned this before, but we don't expect or want the temperature to get wildly higher. So it's only going to go up by maybe 5 degrees, and that's okay. Okay. All right. So when you have taken all of your data, and if you follow the chart that's given to you in the lab handout, it should be like 30 minutes worth of data. You are going to switch off the system and turn off the power supply, remove the belt drive here, and then we're gonna just kind of work in reverse. So I'm gonna take off this lid. And place it back here. I'll undo the electrodes. And then I'm gonna use the same tongs to grab this out again as what we did to place it. Maybe. The lighting in here is a little tougher than it was earlier. All right. So pull this out. Does anyone want to open this for me? Is anybody extraordinarily strong? So I won't let him go for too long because I set him up for failure. This thing is pressurized to 25 atmosphere, right? So it is unopenable in this state. So what I'm gonna do, Yep, so you need to release, you can unscrew that to unrelease the, yep, you can open it more if you want. It's just like a pressure cooker, we're just letting off the pressure that's inside here, and that will let us open up the top. Fantastic, you can close that up. And now it should open. There we go. Much better.
Pressure isn't. That's probably something that happens a lot, isn't it?
Mhm. That's why I make a memorable demonstration of students during the demo, so that you don't get stuck with this in the lab. All right, awesome. So I'm gonna pop that off. It should just lift right up. Is it stuck? Nope. Okay, there you go. And is it gone?
Yep.
It's all gone. So our sample is missing. Behold, I feel like a magician. Behold, it's gone. Okay. So that's good. If you, here, let me take that over here. Thank you so much for your assistance. So we're gonna just put this back to where it was before. If you find that when you open this up, there is still food sample in there, that is not good. So that means you'll have to repeat it. That happens if, you know, you don't have good contact with that fuse wire. If the food sample is entirely unburned, that means that the fuse wire was touching the little cap and it just shorted out. Okay. So we have enough food samples in the event that that happens. Hopefully it doesn't. But if it does, don't panic. It'll be fine. You just have to try again. So now everything is broken down, essentially. What we want to do is we want to measure the amount of fuse wire that's left on here. So it is a very tiny amount. I don't know where it's gone now. So on both sides, we have these tiny, itty bitty tiny amounts of fuse wire left over. You're gonna wanna measure what is remaining using the ruler right here. So record that and then also make sure you record, you know, the uncertainty of this ruler using the half of the smallest tick mark size rule. And make a note of that in your your data collections sheet. And then all that's left to do is dump the water in the sink. Don't put it back into the tank, just dump it in the sink. And then you'll want to dry everything off. And then you're done. Are there any questions about the procedure? Yeah. Is there a chance of you all So, this happened last night too. I suspect that what happens when there's very little fuse wire left over, if you keep your finger on the ignition button for longer than the light, once the light has like turned on, you want to immediately remove your finger because pressing this down is sending electricity through the wire. So, probably when very little is left over, it's just been pushed down for too long. So if that happens to you, that's okay. I would just make a note of it in the lab report that there were, you know, minimal fuse wires left to measure. There still should be something. It's never nothing, but it'll just be shorter if, you know, you held it down too long. And that's just kind of, we're humans doing this, right? So I might hold it down longer than you do, and that's okay. All right, so everything is dried off. So the uncertainty that we care about in this lab is the following. So we have uncertainty for the lumped capacitance. So thermal capacitance of the calorimeter, that uncertainty is already given to you, right? Depending on whether you have bomb number 1 or 2, the plus or minus calories per degree C is given. We have uncertainty in the mass of the food sample. We have uncertainty in the mass of the gelatin. This is provided to you in the sheet on the Google Drive link. We'll have uncertainty in the length of the fuse wire. That depends on, the uncertainty of the ruler. And then we have uncertainty in our delta T measurement. Right, so just remember that delta T is T2 minus T1, so we're gonna have uncertainty for both T1 and T2, right? Okay, so these are the things that you will have uncertainty for. And then these will all kind of go into the uncertainty for ES, right? Through this equation. Okay. The main plot that you are going to make for this lab is a temperature rise curve. Because in our equation, we have everything accounted for that we need to calculate the energy of the food sample, except for delta T. We didn't really talk about that. We just said, well, we've measured it, right? Which is true, but we need to do a little bit more work to get the data from what we've measured into what we need to put into that equation. So you are going to make a plot of temperature in degrees C against time in seconds. And your data should look generally like this. So your data will be very slowly increasing for a while. Then it will pick up. And then it'll level off and start slowly decreasing. Okay. So this slight increase here, you need to find the slope of this line. And we're going to call this slope R1. And it has units of degrees C per second, right? And then you also need to find this slightly downward slope of this line. So the slope of this line. And we're going to call this R2. It has the same units of degrees C per second. Okay. And then we need to find a couple of critical times. So I'm going to call the time where our temperature starts to really accelerate up. This is time A. And then where it starts to taper off again is TB. And then the next time, the next critical time that you need to find from this plot, this is probably the hardest part, is you want to find the time at which we get to 60% of the temperature rise, okay? So if I call the temperature at TB, this is temperature at B, and then I have temperature at A. My temperature at point C is going to be 60% of the way between A and B. So TC is equal to 0.6 TB minus TC. All right. So we identify where that is, and then we find TC. Now, note that you might need to use interpolation to find the time for point C. Yeah. What?
Yeah.
Yeah, sorry. Is that what you were going to say too?
Yeah.
Okay, thank you. So you might need to use interpolation. You beat her to the punch. That's okay. You're keeping me honest. That's good. Okay, so we're going to pull all of this information off of our plot, and then we're going to use the following expression to calculate delta T. So we're going to use TC minus TA minus R1 TB minus TA minus R2 TC minus TB. So you'll use that in equation star. So I'm going to just give this equation a star. Hang on 1 second. I know you're still writing. So this is equation star. Okay. Okay. And this is all that you need to know about the lab. Oh, one thing that I forgot to mention is please return your empty containers to this little clear box because we'll reuse them every year. So don't just pitch it. Are there any questions? Oh, yeah, sorry. This one. Yeah. Are you on my left page?
Yeah.
Okay. Yep, that's where I'll put it.
Alright, so.
Yes.
So do we have to measure the warning? Okay.
No, the length of the wire before should be in the spreadsheet. Any other questions? Yeah.
This changed if it was cold.
Say again?
If the bill was cold.
Yes, so we would get different answers if like we put this thing in a sub-zero freezer and then did the experiment, it would change. But we're making the assumption that everything is at room temperature to start with. That's why we let it sit and mix the water for 5 minutes before we start, just to make sure everything's kind of at equilibrium. Fair question. Any other questions? Okay, well, that's all I have for you. So you are free to go. Good luck with lab 2.